So too late. Um, so last time, does anyone have any homework questions? Yeah. hmm Parallelepiped. Yeah. 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 Yes. Right. We're talking about that stress cube is a limit as the lengths of the sides go to zero. So it's an infinitesimal cube, and yeah, that's the shape it takes. Yep. hmm Yeah. Yeah. Oh, then that, yeah, don't do that. Right. Yeah. No, only the new stuff. Okay. So yeah, anybody want me to help clarify this more than it's very clear in my head, but I can understand why it in the follow through it some stuff was lost. But the idea is so like if on so yeah, when it says 2 weeks ago and you go back 2 weeks, then that's gonna say do this from 4 weeks ago, do this from 2 weeks ago, skip that stuff, and just do anything that's new. And so the way that it's supposed to work is the first time I assign something, you do everything, every number I assign. 2 weeks later, you do half of those again, the evens. 2 weeks after that, you do the odds. And so you'll end up doing every problem twice, but just stretched out over 4 weeks. Yes. Uh, let's just skip it. Yeah. Yeah. Because we've already done the one. Yeah, let's just skip it. Okay. So the next quiz we're going to have is the next one that's listed on the syllabus, and it'll be quiz 3 on the syllabus. Yes. Yes. Only problems. That's right. No summaries. Do the even bullet points of your summary. Yeah. Though all that that's meant to do is make you do all the problems the first time, the evens in 2 weeks, and the odds 2 weeks after that, so that over a span of 4 weeks you've done the problems 2 times to make you keep just revisiting that part of your brain. Any other questions? Okay, so last time we got into the eigenvalue problem. Uh, the topic is principal stresses. And that's an eigenvalue eigenvector problem. And the definition of the problem was we have the stress tensor. And if we multiply the stress tensor by an outward facing unit vector, Then that gives us the traction on that face, the face defined by that outward facing normal. And we're looking for the particular face where the traction is normal to the face. In other words, there's no shear stresses. So this is equal to this times the same normal vector. Okay. And by the way, that's just a different way of writing a constant times this vector. Okay. So another way to think of this is we're looking for a unit vector where you multiply the unit vector by the matrix, and it's the same as multiplying that unit vector by a constant. That's usually not the case, but that's what we're looking for here. Yep.
So all these normal stress
The normal, oh, these you're talking about?
Yeah.
Okay. No, there are going to be three answers to this. And we'll see that that comes from the fact that we're getting a cubic polynomial, solving for the roots of a cubic polynomial. It has three roots, and each one of those three roots is one of the normal stresses. But this is not the principal stress tensor. This is just another way of writing that, so we can start to manipulate it. Okay, so now I'm going to subtract this stuff on the right over here. I'm going to subtract from both sides, and you can do that as sigma xx minus lambda times sigma, not times, then sigma xy, sigma xz, sigma xy, and now here on the diagonal we have sigma yy minus lambda, and then sigma yz, and then sigma xz, sigma yz, and then on the diagonal sigma zz minus lambda. And all that times this outward facing normal vector is now equal to the zero vector. Okay. So we subtracted this from both sides. It turns out that you can associate these matrices the same way you do with constants, And so basically we're taking, so we have this times this vector minus this times this vector. We can just pull that matrix, add those two matrices together, and we come up with this. Anybody want to go into detail on that, or happy enough? So what does it take for this to be true? So we want lambda and a unit vector that satisfy this equation. Well, what we don't want is one solution would always work. The inverse of this matrix, okay, if there is an inverse of this matrix, we could just left multiply the inverse of this matrix here, multiply it over there, and then that equation works, right? Because inverse times this makes those go away, and you just have this is equal to 0. And we don't want the solution where that vector is just equal to 0. So the solution we're looking for is where this is not invertible. Okay. So the left matrix is not invertible. Anybody remember the rules for it has to be true of a matrix if it's not invertible? Anybody ever seen that in linear algebra or anything? The determinant has to be equal to 0. If the determinant is equal to 0, matrix is not invertible. So we're going to require that the determinant of the matrix is 0. Okay, so so the way you calculate the determinant is, so I'm going to take this value here, and then I'm going to cross out its row and its column, and I'm going to multiply this times the determinant of the stuff inside. So this times this minus this. I'll write it out. So sigma xx minus lambda and then if we cross these out, we're going to go sigma yy minus lambda times sigma zz minus lambda minus sigma yz times sigma yz. So now this times this minus this times this. So sigma yy minus lambda times sigma zz minus lambda minus, in this case, we have sigma yz squared. Okay, and now we're going to go to the second one. So now we're going to multiply by this term. So, and this is minus, so minus sigma xy times the quantity, and we're going to cross out this row and this column, just like we did before. The row, excuse me, the row and column associated with that element. Now you don't get your quiz because you're late. And now we're going to take this times this minus this times this. Okay, okay, you can have your quiz later. Okay, so sigma xy times the quantity sigma zz minus lambda. Yeah, I did. So sigma zz minus lambda. And then minus sigma xz times sigma yz. And then plus, now we go to the last one along that row. So now we're going to multiply everything by sigma xz, cross out this row and column, and multiply this times this minus this times this. Okay, so we have sigma xz times the quantity, sigma xz times, no, xy minus yz. And then minus xz times the quantity sigma yy minus lambda. And we're setting all that equal to 0. Okay. So that's what's required for this matrix not to be invertible. And then, because if it's invertible, there's a trivial solution. We don't want that. And so this is our requirement. And what's so the variables that we're looking for here. So this is a single equation. The variable we're solving for is lambda. So what kind of equation is this? It's a polynomial. If you multiply all this out, what's the order of the polynomial? So every one of these you're multiplying lambda, lambda, lambda. Well, I guess that's the only one in this one. But yeah, there's the third order, the third power of lambda. And so there's 3 roots. And each root of this polynomial is 1 principal stress. What if one or some of the roots are complex? You can have complex roots of a polynomial. And then what does that mean if you have a complex stress? Well, I mentioned before, it doesn't happen because the stress tensor is symmetric, and symmetric matrices only have real eigenvalues. Once you have your 3 lambda values, plug them back into the equation one by one, and solve for the corresponding eigenvector. Okay, so let's do an example. Oh, so this is, okay, so I went through this whole like derivation where this comes from. You can do this calculation by hand, and I'm going to show you how to do like one simple one by hand. But how do you do this on a, how do you do this in practice if you really just want the answers? You say like eigenval. This is the notation you use on a TI-89. You know, if you're in MATLAB or Wolfram Alpha, there's some different way of doing it. But basically, you just tell your calculator or your program to give you the eigenvalues of the stress tensor, and it gives you the three principal stresses. And then you're done. Okay, so no, not a very good one. So I'll give you on exams. I'm going to make these. Okay, so cubic polynomials are a pain to solve. Right? You can do them like using a Newton's method or something, but there's no closed form solution for a cubic polynomial. But quadratic quadratic equations are easy to solve. So on tests, I'm just going to make one of the eigenvalues 0, you know, and so then all you have to do is solve a quadratic equation, which you can do easily, and so it won't be too hard for people who don't have a way to do it here. But this is the thing to remember, is that if you want to calculate the principal stresses, you just go to the nearest program or website that'll calculate eigenvalues for you, enter in the stress tensor, and it spits out the principal stresses, and that's all there is to it. Okay. Um, all right, so let me do an example. I guess I'm going to do a couple examples. The first one is kind of uh, so we're going to start with the stress tensor 3, 0, 0, 0, negative 5, 0, 0, 0, 0 in megapascals. And we want to calculate the principal stresses. So we want to calculate lambda 1, lambda 2, and lambda 3. And then each one of these has its own corresponding outward-facing normal, which is going to tell us the orientation of this new principal coordinate system. All right, well, who remembers what the definition of the principal stress tensor is? What are we really looking for in the principal stress tensor? Yeah, the shear stresses are 0, so we're already starting with a principal stress tensor. Okay, so we're going to go through this calculation, and it's going to give us back 3, negative 5, and 0, should. And it's also going to give us back axes that correspond to our axes right now. Okay. Okay, so this is already in the principal coordinate system. Okay, so what do we expect our n values to? So we expect lambda 1, lambda 2, and lambda 3 in any order to give us 3, negative 5, 0. And what do we expect our n vectors to be? Yeah. Yep, exactly. This will give us 1, 0, 0. The one corresponding to -5 will give us 0, 1, 0. And the one corresponding to 0 will give us 0, 0, 1. It could also give us the negatives, and I'll talk about that in a second. But it turns out if you ever, well, it's perfectly fine for this to come out as -1, 0, 0, -0, 0, -1, 0, whatever. It's not going to matter. I'll talk about that after. So what we want to do is calculate the determinant of 3 minus lambda, 0, 0, then 0, -5 minus lambda, 0, 0, 0, and then this one's 0 minus lambda, so just negative lambda. And the notation for determinant is like absolute value. All right, so to calculate this determinant, we have the quantity 3 minus lambda times the quantity -5 minus lambda times negative lambda, and then minus 0 times 0. Now we're done with this one. We'll go on to the next value in the row, and we're taking 0 times, doesn't matter. So minus 0 times something, that's going to go away. And then plus 0 times something, so that's going to go away. And we're setting all this equal to 0. So that's not there, and that's not there. Okay, so we're looking for the roots of this equation. 3 minus lambda, -5 minus lambda, negative lambda is equal to 0. What are the roots? Yeah, right, it's already factored out for us. So if lambda itself is equal to 0, then this holds. If lambda is equal to -5, it holds. And if lambda is equal to 3, then it holds. Any questions about that? Let's go through these. So now we're going to find the eigenvectors, the outward-facing normals for our new coordinate, our new stress cube. And we're going to find one of these for each one of those eigenvalues. So first I'll say lambda is equal to 3. It doesn't matter what order you do it in, but I'm going to do it in the order that corresponds to our original one. Okay, so we have 3 minus lambda, and I'm going to plug 3 in for lambda. So 3 minus 3, 0, 0, and then 0, -5 minus lambda, which is 3, 0, and 0, 0, 0 minus 3, and we're multiplying that by nx, ny, and z, and that has to be equal to zeros. So this matrix comes out to be 0, 0, 0, 0, -8, 0, 0, 0, -3. Well, the first equation doesn't give us anything. So first one says 0 equals 0. That doesn't help. But the second one says -8 ny is equal to 0. So does that tell us anything we can use? Yeah, we're trying to figure out what these values of these n components are. And so this one tells us that ny has to be equal to 0. And now we'll go on to the third equation. And it says -3 nz is equal to 0. Does that tell us anything? Nz has to be equal to 0. So what's a unit vector? You know, this first one is a unit vector where ny and nz are both equal to 0. Unit vector is that. Yep, it could be 1, 0, 0, or it could be -1, 0, 0, and those are the only two possibilities. Those are the only two unit vectors that satisfy those restrictions. Yep. Because it's an outward-facing normal unit vector. But also, with any eigenvalue and eigenvector problem, there's an indeterminacy like this, and those eigenvectors can be in either of the two directions with any magnitude. And so usually just as like for us, the unit vector actually represents something physical because we're talking about these outward-facing unit normals. But in general, people just usually use unit vectors because then you can scale it to any length. Like it just gives you something consistent. Okay, so what do we want to do now? Yeah, right. So now we're going to go to lambda is equal to -5 and calculate the n vector that corresponds to this. So we have 3 minus -5, 0, 0, then 0, -5 minus -5, 0, 0, 0, and then 0 minus -5. And this has to be equal to 0, 0, 0. And so I'll rewrite this as 8, 0, 0, 0, 0, 0, and then 0, 0, 5 times nx, ny, nz is equal to the 0 vector. So the first equation says 8nx is equal to 0. Does that tell us anything useful? nx is equal to 0. Second equation, nothing. Third equation says 5nz is equal to 0. So nz has to be equal to 0. And so what's a unit vector that meets those two requirements? Yep. So n has to be equal to 0, 1, 0, or 0, negative 1, 0. And then the last one is for lambda equals 0. So we have our matrix is 3 minus 0, 0, 0, then 0, negative 5 minus 0, 0, then 0, 0, and then 0 minus 0. And that times nx, ny, nz is equal to the 0 vector. Okay, so equation 1 says 3nx is equal to 0, and so nx has to be equal to 0. Equation 2 says negative 5 ny is equal to 0. So that says ny has to be equal to 0. Equation 3 doesn't tell us anything. And so the only two vectors, the only two unit vectors that meet these requirements are n equals 0, 0, 1, or n equals 0, 0, negative 1. Yes.
We don't know let's go back to the first one.
Okay.
We don't know what NX is.
Right.
So we look at the normal vectors there. Normal vectors.
Mhm.
How is it that we can just say that NX is equal to 1 negative 1?
And not a million or pi or e or whatever. Okay. Yes. Any number solves it for nx. So we just scale it to a unit vector just for consistency. And that's how your calculator will give it to you, or a website will give it to you. But yes, negative 8 million would work fine too. You just end up with an extra factor of negative 8 million on both sides of the equation. Physically, it makes more sense for us to remind yourself that where this came from is that we're multiplying the stress tensor by an outward facing unit normal vector, because that gives us the traction. But in every eigenvalue problem, in any eigenvalue problem, one thing that comes up in every eigenvalue problem is that this problem is solved by eigenvectors that have an arbitrary scaling factor like that. So let's just choose 1 as our length. Yep. Mm-hmm. No, that only worked because we started with the principal stress already. So if we have a case where it's going to end up being the principal coordinate system is rotated 20 degrees from from our original one, then it's sort of a mess. But still, you have a system of equations you can solve to find out what the direction is of that unit normal. Okay. Why now? Why doesn't it matter whether, like, for example, n is equal to 1, 0, 0 or negative 1, 0, 0. Okay. You may be asking yourself. Just kidding. No one cares. Okay. But I've come this far. Can't come this far without going a little farther. So imagine a stress cube. I'm just going to make up some arbitrary stress cube. Okay, so let's say that this is 5. Let's say that this is 2. That means this is 2. And let's say that here there's 10. Okay. If the coordinate system is what we're used to, what's the stress tensor? Okay, so the axes look like this. Here's x, here's y, here's z. Okay, so stress in the so on the x face, in the x direction, we have positive 5. In the y direction, we have negative 2, then 0, then symmetry, then nothing for the normal y, nothing for yz, then 0, 0, negative 10. Okay. Now I'm just going to switch let's see, can I switch all of them? X, Y. I'm going to switch 2 of them. Now, same stress. Cube, but the axes are x, y, z. So just arbitrarily flip the signs of 2 of those axes. Okay. So now the stress cube we have, what did I say, 5, and then 2, and then 2, a little straighter, and then 10. Okay. This time the axes are like this. There's x, there's y, and there's z. Okay, so now on the positive x face, what's the normal stress in the x direction? So that's that face sort of behind there. Have you ever heard of the game Crystal Castle, video game from the 80s? If you ever see that somewhere, and you just, like, right at the start of the game, just wander behind this positive, what's our positive x face here, wander back there and hit the jump button, it skips you like 100 levels and gives you like 100,000 points. No, it used to be an arcade game. Um, okay, so what's sigma XX? Positive 5, right? Even so, this is the reason I did this. Even though we arbitrarily switched the direction of the x and y axes, the relationship between the stress cube and the stress tensor stays the same. And that's why it doesn't matter whether you choose your eigenvalue positive or negative. All you have to do is choose them in such a way that the coordinate system is right-handed. Okay, so same thing with the, okay, so which direction is the y component on the positive x face? Yep, it's -2, then 0, and then -2, 0, 0, and then 0, 0. That one's still the same. So this is the same. So switching axes to the opposite directions didn't affect the stress. Okay. Now give me 1 minute to sum this up, because I just all of this is kind of like background information, because eigenvalues and stuff are going to be important to you going on. But practically speaking, here's what you need to know. So practically, for this class, you'll be given stress tensor. The eigenvalues of that stress tensor are the principal stresses. And the eigenvectors of that stress tensor are the axes principal coordinate system. So a lot of you are going to go, well, all of you are going to transfer somewhere. And no matter where you go, I suppose, there, some of the professors that you'll encounter are going to say, like, they're going to say use Moore's circle. Okay, this is the thing, Moore's circle, to calculate the principal stresses. And once a long time ago, that was how you had to do it. It was a graphical method. You had to be very careful with your graphical approach and measure stuff and whatever. But that was a long time ago. So just say this. My professor taught us eigenvalues because they make electronic digital calculators now. And if you need a sign note or anything, then come talk to me. I'd be happy to give you one. Any questions? Yes. That has to do with the, yeah, like that compares the angle to the stress. Nope.